Hello. In today's video, we're going to be talking about applications of rational functions. We're going to be using a cell phone problem as an example and talking about how the distance you are from a cell tower might affect your cell signal. There are many resources online on how cell towers work and how they affect your cell service given your location and where your house is and where your work is. This YouTube video, How Cell Towers Work Hands-On from Mr. Mobile on YouTube, would be a great resource to check out, and I highly recommend it. Now let's talk about the problem we asked here. So we are being asked this are told that the strength of a cell phone signal is related to how far you are from the nearest cellular tower. For a given signal, the product of the signal strength and the square of the distance d squared is constant. In our first question, we are being asked, since the product must be constant, and we can maybe highlight that part that we just mentioned there in yellow, it's going to be very important that for a given signal, the product, we want to highlight that in yellow. So the product of the signal strength and the square of your distance d squared is constant. So if you have two things being multiplied by each other and the answer is always the same, if one of the two variables goes up, the other has to go down. For instance, if you knew that, say, 4 times 4 is equal to 16, if one of those 4s went down to a 2, the other one would have to go up to an 8 to still equal 16, and vice versa. If I instead went from 4 and 4 up to 1 went up to 16, the other would then have to go down to 1 from there. So what we would basically see in this question is the following. To answer this question, I would say if the distance increases, the signal strength must decrease. It's got to equal the same thing when they are multiplied. So if one goes up, the other has to go down. We are now on question number 2. For a particular phone, the signal strength is measured to be 75 units when the phone is 2 kilometers from a tower. If the same phone is used at 4 kilometers, what will the signal strength be? So for this, we're going to use some equations and stuff here. So we need to think of this, well, if I know that the product, let's go back to the top, the product of the signal strength and the square of your distance squared, and the square of your distance is constant, well, that means that I would have something like 75 times 2 equal to a constant. So if that's true, we would just need to figure out, well, what is that equal to? Well, if we our calculator, 75 multiplied by 2, that equals 150. So our answer here is 150 for our constant. We are now on number 2. For a particular phone, the signal strength is measured to be 75 units when the phone is 2 kilometers from a tower. If the same phone is used at a distance of 4 kilometers, what will the signal strength be? So let's look at the first part. We know that the product of signal strength and the square of distance has to be constant. That's important. So we're going to first do 75 times, which is our signal strength, times our distance squared, 2 squared. And that is going to give us whatever the constant is that they were referring to. And if we put that into our calculator and do 75 times 2 squared, we get an answer of 300. So it turns out for this problem that our constant is equal to 300. Now that 300, obviously, as the name suggests, is not going to change at all. So let's look at the second part of the question. If the same phone is used at a distance of 4 kilometers, what will the signal strength be? So in this problem, we don't know what S is. We have an unknown S, and that is being multiplied by our distance 4 squared. And we know that it still has to equal the same number. In this case, it is 300. And so let's kind of keep going here. And so if that is true, we can divide both sides of this by 4 squared. So that would give us an equation of S being equal to 300 divided by 4 squared. And that ends up, let's check what that equals. We have 300 divided by 4 squared. And 18.75 is our answer. 18.75 would have to equal our signal strength. And that completes question number 2. We have found out that signal strength is equal to 300 over 4 squared, equal to 18.75. And we've also realized that we can say that our answer for number 3 kind of comes from that too. Write an equation expressing signal strength as a function of distance for this particular phone. So if we wanted to come up with that equation, we would just take this equation we used last time. We know its signal strength is equal to our constant of 300. So if we want to type out this equation nice and neatly, we would have S is equal to a fraction of 300 being divided 300 being divided by our 4 squared before, but now it's just distance squared. We have our equation right there, and if we wanted to use this in function notation, which is a good idea to practice, we would have signal strength as a function of distance, and that is equal to the fraction of 300 being divided by distance squared, as a more technical way of writing it. Now that we have our equation here, let's look at Desmos graph of this equation and take a look at a reasonable domain. That's very important, because reasonable domain is very important for word problems. And so we have that as our result there, and we want to include all appropriate labels as well. So let's look at our graph. We know the distance d is in kilometers. We have our x-axis labeled as that. Signal strength in units, to keep it simple, is our y-axis. And we can tell that we have a graph here that as distance is increasing, x goes to the right, our signal strength is going down, and vice versa. That matches the relationship that we heard about in our earlier question. We are now on number 4 on this assignment. The number 4 states the call will be dropped if the signal strength is getting below a certain limit, being 3.5 units in this case. And we want to figure out the maximum distance for which a call can be completed in this case, assuming no other variables or interference otherwise. So the first way we can do it is algebraically. So the way we want to do that is if we come up here to insert an equation, we would basically have something where our maximum is 3.5, and we can just kind of solve for that being the signal strength. And signal strength is the y, so we have to put it in for y equals to 300 divided by d squared, 300 over d squared. And so we just need to solve that equation for d. So the first thing we do is multiply both sides by d squared. And so let's put that equation in first. So then we would have 3.5 d squared is equal to 300. And then we would divide both sides by 3.5. So let's put that in. So we have d squared is equal to 300 over 3.5. 300 over 3.5. And then you would take the square root of both sides. And so that would mean we'd have an equation of d is equal to the square root of that fraction of 300 over 3.5. And we can go to our calculator to figure out exactly what that is equal to now. So we're going to do the square root of 300 divided by 3.5. The square root of 300 divided by 3.5. And the answer is 9.26 rounded. And that is equal to how many kilometers that it would be the maximum distance, 9.26 kilometers for distance. The other way to do this is graphically. So look back at my Desmos graph here. We have our equation, and if we're looking for when y is going to be 3.5, or the s in this case, so we could say even s equals 3, y equals 3.5. And we would just come down here to where they're intersecting, giving us the same answer. As the distance got longer, now our signal strength got below 3.5. So anything to the left side of that point would still be good. The signal strength would be bigger than 3.5. Moving on to our last problem. According to your model, what will the signal strength be when you're staying right next to the tower? Explain whether or not this answer is reasonable. So if we look back at our graph, the signal strength would be really big if we were really close, really small kilometers. So if I entered into our function up there, if we did s of 1 kilometer, well, that means we have a signal strength of 300. If we did a tenth of a kilometer, it would be 3,000. If we did a hundredth of a kilometer, well, that would be a signal strength of 3 million, but that is not really very reasonable to have a signal strength of 3 million. As you get closer and closer to the cell tower, you would be able to understand that, well, my signal strength is not actually getting better if I am 12 feet from the tower, or if I'm 2 feet from the tower. That is essentially, for our purposes, exactly the same. And some just notes at the bottom here is that cell tower transmits a signal with a fixed amount of energy, and that energy gets spread out over a greater and greater area as it goes farther away. An area is proportional to the square of the distance, not the distance itself. And in reality, these energies that are going out in all directions are getting muddied by other buildings, by mountains, by other things like that. So we kept our model simple by ignoring some of those extra variables. And this is a great example of how to model a real world situation using rational functions. We had variables in the denominators of our function, the main one we used that I've just highlighted. And this will be something to base other problems on. Thank you for listening.